going to divide this equation by 1 over y. Or we're going to divide it by y, meaning multiply it by 1 over y. Okay, so we're going to do that to this side, and that will yield this thing also. Divided by 1 over y. Okay? And we'll define x is just defined to be 1 over y. Okay? So our new equation, this way it's the same. Remember, this is just a proportionality equation. Will look like this. It'll be x times c MC HMH OMO. Okay? And then it'll be 1 O2 and 3.76 N2 will yield XMC plus X times MH over 2, okay, and then this will be, it'll be plus 1 minus X times YCC, and that'll be O2, and then plus 3.76 N2. Would you all agree with that if I multiplied this equation by 1 over y defined to be x? Would you all agree with that? Okay. So before, the way we were considering it on a proportionality basis, you know, conceptually, that's what we were doing, but equally well, we could say that in effect, we have 4.76 moles of air coming here for every x moles of fuel. Okay, so we have x moles of fuel that are put in here, right? X moles of fuel for every 4.76 moles of air. It's a different way of looking at it. All right, so this is how much air is coming in at proportionally x moles of fuel for however, every time we have 4.76 moles of air processed here, we inject x moles of fuel. Same gig, right? And if you go through the same procedure, the same first law that you went through to get this equation, okay, and actually this equation, if you do the same energy balance, the enthalpy of the reactants equal to the enthalpy of the products, and all the adjustments that you did to get equation 2, what you'll get is, instead of equation 2, you'll get equation 6, okay? And equation 6 can be solved just in terms of x, if you will, okay? And if you, here's equation 6 is your mass balance, and then your first law that's equivalent to equation 2 is equation 7, okay? And it looks very much like equation 2, okay? And if you solve it for x, this is what you get. And would it be a surprise to you that equation 8 is just the inverse of equation 3? Okay, if x is 1 over y and y is this, then x is just going to be the flip of this, right? Did you all buy that? Okay. So conceptually, we're going to view it like this, like I just showed you. This is just because I think it's conceptually easier to figure out what's going on with the afterburner. okay? Because with the afterburner, I want to add fuel for the given amount of air that we already have, okay? So I want to change the thinking of it, that's all, okay? So do I need to set up new stuff, okay, to calculate X? Do I need to do a new program to calculate X? Or if I want X and I have a program to do Y, can I not just do a little statement that says X is equal to 1 over Y and I'm done? Okay? So this is no big deal for the main burner, all right? When you all are modifying your pure turbojet without afterburning, to do afterburning, all I'm asking you to do is to compute F the way you did it, okay? And that will be your F based on your fuel-air ratio that the main burner sees, okay? So just compute Y and compute F for the main burner. It's your fuel-air ratio for your main burner, okay? And you're going to need X for your afterburner calculation. But don't program up this equation. Put in one little statement. X is equal to 1 over Y. Okay? You with me? Okay? So that's easy enough. One statement. X is equal to 1 over Y. Okay? Now, if you add afterburning, okay, here's how we're going to look at it. You add afterburning. With that concept in mind, as we know, this is TR that is computed for this burner, and this is given as your turbine inlet temperature. Okay, so you're able to do your calculations that way. You're going to come over here, and here's your afterburner. So I'm saying this is your combustion chamber, also known as your main burner. And then over here you have your afterburner. And T06 will be your TR for this one. You'll know the temperature of the reactants. And T07 is going to be your temperature of your products. And I'll also call that the temperature of your afterburner, and I'm going to give you that temperature, so you'll know your products of combustion. So based on 4.76 moles of air coming in here initially, what Z is going to represent? Z is the additional fuel. It's the additional moles of fuel added to the afterburner. Okay, for each 4.76, not Y, for each 4.76 moles of air, original air. Okay, so Z for your afterburner is what X is to your main burner. Okay, and you're going to need to know what Z is. Okay. And the reaction equation that you have going on here looks like this. The products of combustion from your main burner, the products of combustion from your main burner are your reactants for the afterburner. So if I look at, and I'm doing the afterburner now, and I'm looking at the reactants, and then the products. Okay, so what do I have coming in here? Alrighty, I have this stuff. Okay, this is the reactants. This is the products of the main burner, and it's the reactants of the afterburner, right? Okay, all based on 4.76 moles of air. Okay? So, the reactants will be all that stuff. I guess it's X MC plus X MH over 2. And this is XMC CO2. That's how many moles of CO2 I have for every 4.76 moles of air that are taken in. And this is how much water I have. Okay, X times MH over 2. Okay, and then I have nitrogen, and I have oxygen, right? So I have 1 minus X YCC moles of oxygen, okay, and I have plus 4.76 moles of nitrogen. And what I'm adding is Z moles of fuel. So I have Z CMC HMH OMO plus. Okay, so I add, so these are my reactants. I have Z additional moles of fuel that I throw in here to the rest of the stuff that is down here. Does that make sense? Okay, so there's your reactants. Okay, and this is going to yield, it's going to yield the same thing. Products of combustion will be CO2, H2O, O2, and N2. And here's what it'll look like. If X moles of fuel, okay, in the original reaction generated X times MC moles of CO2, then what you're going to have here is X plus Z times MC moles of CO2. That'll be the effect. It's the same effect as if you originally added X plus Z moles of fuel, if that was actually how much you actually had. Okay? And then over here, you'll have X plus Z times MH over 2 H2Os. Okay? So as a consequence of the combustion turning the carbon and the hydrogen, okay, and possibly the oxygen in the fuel, to carbon dioxide and water, you get additional carbon dioxide and water in the fuel, okay, because of the additional combustion. In other words, this oxygen over here is going to combine with these things over here to give more carbon dioxide and more water. And then on the oxygen itself, that's going to cost me oxygen. And if I look at this thing right here, what I have is how much oxygen did I originally have? 1. And on the first combustion, I lost X minus YCC. So on the next combustion, it's going to be Z times YCC moles of oxygen. And then the nitrogen is inert. So this is just plus 4.76 N2, not Y, just 4.76 N2. Can you see how I was able to do that just pretty much by inspection? Did you see what I did? So this is now your products of combustion. Okay? So if you look at this equation right here, I'm able to do my mass balance by inspection. I can also do my conservation of energy by inspection. It follows that. Okay. Here's my conservation of mass. is what I just wrote up on the board. You saw what I did, hopefully. Okay? I just looked at the original main burner equation, and logic concluded, that I had to start with everything that I had on the outflow of the main burner, plus Z moles of additional fuel, and then I could see how X was distributed amongst the products. So if I throw in Z more, the effect is just X plus Z. Does that make sense? Okay? And then similarly, if I look at this equation right here, as this one right here, as my energy balance equation, okay, for which I solve for X, okay, I can look at this and go, now I've got an additional Z that's happening, but my changes in H now are not between T03 and T04. Remember, these delta H's were the change in H for the products of combustion between T sub P and TR for the main burner. When I'm looking at the afterburner, these delta H's are for the this equation, the delta H's were basically T sub P and TR for that were T04 and T03 respectively. Now when I'm looking at the the afterburner, okay, TR and T sub P are T06 and T07 respectively. So you got to know what these delta H's are always based on the temperature of the reactants, temperature of the products concept. So if I look at this, I can modify this equation and then this equation for the afterburner to give this. Okay, this is my actual conservation of energy equation. You compare this, okay, with equation 11, conservation of mass for this auxiliary burner, and then see what you did, okay, with 6 and 7 in the main burner. Then by direct analogy, then 11 and 12, conservation of mass and conservation of energy for the main burner will look like this. Okay, so this equation right here, the only unknown in it is Z. It's the only unknown. And the delta H's are for the afterburner, between TR and T sub P for the afterburner, which will be known. You need to know X from the main burner. You must know that. Okay? What is X? 1 over Y. So to add this afterburning capability, you're going to have to add this equation. And you'll need to know X, but X is just 1 over Y. So your little statement X equal 1 over Y takes care of that, but you're going to need to solve this equation for Z. And doing that for you, doing the algebra for you, the bottom line, if you will, as they say, is here it is. Okay? Here it is. Okay? So you will have to add that equation to do afterburning. So far, 2 equations, right? X is equal to 1 over Y, that's the first one. And then this is the one that will require a little bit of programming. Now, most of what it is, of course, you have X in it. Everything on the right-hand side of the equation is known. Most of what it is being able to calculate delta H's, right, for those 5 products of combustion. And the delta H's are between TR and T sub P. And you need to understand that because Z is for the afterburner, you need to be using T06 and T07, okay? Is that clear? Okay? So Z, this is all of homework 7 is about adding this equation, calculating Z. One equation, okay? And then fuel-air ratios, F, okay? This is the fuel-air ratio associated with the main burner. There's the ideal calculation. The CC means main burner. Gives you your actual F, okay? And using a combustion efficiency for your main burner, okay? And so this thing right here is how you compute the actual F ideal, and this factor down here in the denominator is how you make it F actual for the main burner. And notice that it might be useful to think of it in terms of y, 1 over y is x. Okay, so one way to do it, if you go through the, all the algebra, okay, is x is ideal. That's the ideal fuel put in for every 4.76, not y. X moles of air, fuel, for every 4.76 moles of air. That's your actual molar fuel-air ratio ideal. You divide it by this burner efficiency. This increases how much fuel you do. You're correcting this ideal model. And then this has it on a molar basis, and then you use your molecular weights of your fuel and air to put it on a kilogram basis, okay? Now similarly, you can define an F just for your afterburner, okay? Based on how many moles of fuel that you added to the total air you had originally. Okay, and it looks just like, the F for the main burner, CC meaning combustion chamber. Both of them are combustion chambers. I wish I'd gone MB, main burner. Okay, so you can compute one using X and the other using Z. Okay, and then the total F, okay, considers the total fuel burned, right? Your actual F overall. Okay, your F overall is the sum of the two, because both of these F's are scaled to the same air, 4.76, right? This burner efficiency is increasing this one to make it more realistic. This one's increasing this. All based on 4.76 moles of air, and these molecular weights put it on a kilogram basis rather than a kilomole basis. So there you go. So that's how you would compute your fuel-air ratio with afterburning. You need to compute X and Z, right? So here's the summary of how you program this up. Main burner, no difference. Calculate Y, then FCC ideal, and then F actual, okay, for the main burner, okay? Now when you go into the turbines, okay, nothing's going to change in terms of how you do the calculations. And if you look carefully at turbojet, you were using your F from your burner calculations to account for the fact that your turbines were not operating on air anymore. They were operating on a mass flow rate based on the air ingested and the fuel that was injected in this burner. So since that's the basis that it was calculated on, you want to use this F calculated just considering the main burner when you're doing your turbine calculations. So that would represent no change, okay? No problem. To add afterburning, you're going to know what T06 is. I'm basically going to give you T07. You want to know X here, okay? So you have your statement X is equal to 1 over Y, and you solve equation 13 for Z. So it's that little equation, X equals 1 over Y, plus equation 13 that you have to add. Okay? And then you compute F overall using equation 14, or if you want, you can compute, you already know FCC, you can just compute FAB based on Z in these quantities and then add the two together. But you're going to need an F overall. Okay? And then you will use your F overall in your nozzle. Okay, because now your nozzle is operating on everything. You know, 4.76 moles of air, Z moles of fuel, and X moles of fuel. The nozzle is expanding all of that, right? So your F in your nozzle calculations will be F overall. So you go ahead and compute your FS, and then your TSFC is F overall divided by FS. There's one thing missing. One thing missing in this. Anybody know what's missing? There's a particular stagnation property that's missing in this. What's that? Yeah, coming out of my main burner. Coming out of my afterburner. Remember in the main burner, I gave you that, but you also needed P04 to move into here, right? And we know that combustion is going to cause you to lose stagnation pressure from here to here. So I gave you a stagnation pressure loss factor of 4%. Okay? You're going to know this, and you're going to know P06, and I'm going to give you your afterburner temperature. Basically, I'm giving you your flame temperature, right, in what we do. Okay, but to drive the nozzle, you're going to need P07. And it's certainly going to be a lot. It's going to certainly be it's certainly going to be a loss in stagnation pressure due to friction and effectively heat transfer. Combustion has the effect as if you're bringing, on the stagnation properties, as if you're bringing in heat from the outside. Okay, and we know from basic gas dynamics, if you've had that course or made, that heat addition causes stagnation pressure loss. Okay, so I'm going to give you some stagnation pressure loss factor on that. Isn't this fun? It's easy enough, isn't it? So that's how the calculations are done and the theory behind it. It is just kind of a change in philosophy in terms of before we set up our conservation of mass and conservation of energy on the basis of, okay, for every 1 mole of fuel, how much air do we have to make things happen the way we're specifying, right? I mean, that's the way we looked at it. It was all a proportionality thing, all right? We don't actually know how much air we have going. Depends on how big the capture. Cross-sectional areas. Depends on how big the engine is, right? It depends on the area of the inlet, right? We don't know what actual mass flow rates are. We just know proportionalities, okay? So we set it up on the basis of for every 1 mole of fuel that is burned, how much air, okay? And in particular, how much oxygen, which was Y. And then knowing the oxygen, that we knew the air was 4.76 times the oxygen number, right? I thought it was conceptually an easier way to do it, to reassign the basis on which we looked at our proportionality and said, for every 4.76 moles of air, for every 4.76 moles of air, okay, how much fuel do we need to make the same thing happen? Okay, and that how many moles of fuel for every 4.76 moles of air was given the variable name x, and can be shown to be equal to 1 over y from the previous perspective, okay? And then I think that makes it easy to go. Now, based on that, if we put in x here, then, fuel here, then how much more fuel do we add in the afterburner? That's the reason for the change. So, right here I mentioned the fact that stagnation pressure loss in the afterburner was handled with a given loss factor in terms of a percentage for the main burner. We're going to do the same thing for the afterburner. Okay? Isn't this fun? See how we're doing for time. 15 minutes. Okay. Afterburner example problem. The numbers that you get here will represent a benchmark. Okay, that you should match before you attempt to actually do the homework 7 assignment. You should make sure your program is working. Okay? And what we're going to do is we're going to do the exact same turbojet problem. Everything the same. Everything same isentropic efficiencies, same fuel, same turbine inlet temperature, same everything, same flight conditions, except at the critical point we're going to add our afterburner. Is that clear? So here's our afterburner. We've added going all the way back to the example problem, which was your model for homework 5. Okay, everybody got that? And remember, coming into your nozzle, now coming into your afterburner were these stagnation conditions. So T06 is the temperature of the reactants for your afterburner. And P06 is your stagnation pressure entering here. And here's some stuff that we calculated. Here's our actual fuel-air ratio for the main burner, corrected for the burner efficiency. And it came by dividing F ideal, which was this number right here, calculated using Y. Okay? It came by dividing that by 0.98. So here was your original actual corrected F for the main burner, and here was your, what came out, basically what would come out of homework 3, part 1. Okay, and I don't know if I showed this in the previous stuff, but this was based on a Y calculation of 86.9913. So X is 1 over that, and here it is. Okay? So coming into our afterburner, the temperature of the reactants now for our afterburner is T06, and the temperature of the products, let's say that we're going to reheat up to 2000 K. Okay? Much higher than any modern turbine for a gas turbine engine can stand. The reason we can go so much higher is because we can build everything stronger. And the turbine has to have these thin, aerodynamically efficient blades that are restricted in terms of how much thermal energy they can take. Okay, it wouldn't even be necessary to do afterburning if the turbine could take it right in the main burner. Okay, so we can reheat to much higher than the original high pressure turbine could take. So this is a specified number. This is your flame temperature, if you will, 2000 K. And so with TR, T sub P, and X known, we're able to solve equation 13. This is the main equation you're going to have to add for afterburning. Okay? And that gives this value for a Z. Okay? And then F overall, okay, based on equation 14, okay, uses X, Z, and your individual burner efficiencies. And I'm going to take your afterburner efficiency to be the same as the main burner. And if you wanted different values, you could specify them in this equation. Okay, so this is basically your fuel on a molar basis. Ratio to your air, 4.76. So this is your fuel-air ratio molar in a molar sense. When you multiply by the molecular weights of the numerator and denominator, respectively, you get that as a fuel-air ratio overall on a kilogram basis. So this is your F overall. And then using the same stagnation pressure loss factor of 4% of the delivery pressure that we used in the main burner, that means we only retain 96% of our stagnation pressure. We're probably losing significantly more than that. Here's our adjusted stagnation pressure for our nozzle. Okay, so this is what's going into the nozzle. Lower stagnation pressure, very much higher stagnation temperature. Okay, we go in and we do our nozzle calculations. That involves a choke test. We find our nozzle is choked, and so we need to find the pressure at the exit, the density at the exit, and the flow speed at the exit in a similar manner, but with different stagnation conditions. These numbers are very different. Okay? Calculating FS and TSFC. Here's FS, and here's TSFC using F overall. Okay, here's the comparison. Here's the difference. FS with afterburning, FS without. It's almost twice the thrust per kilogram of air processed. And here is the TSFC. It's getting up there in terms of twice. Okay? Now that can be very misleading. Okay? When FS doubles, basically your thrust is doubling. But when your TSFC doubles, that does not yet mean that your fuel consumption is doubled. You need to look at that very carefully, okay? If I were to scale FS with afterburning over FS with no afterburning, that does give me the ratio of thrust afterburning to no afterburning. And that came out to be 1.74, so I got a 75% increase in thrust. If I scale my TSFCs in a similar manner, I get a 75% increase in TSFC. Okay, but what is the fuel consumption actually doing? Okay, if I look at my fuel consumption, mass flow rate of my fuel to the mass flow rate of my air for the afterburner, with afterburning, I mean, not for the afterburning, but with afterburning. That's given as F overall. If I look at that same ratio, okay, when I'm not running afterburning, then these two ratios are just calculated by my afterburning F and my no afterburning F. That's what these are. So if I want to look at my actual fuel flow rate, afterburning and no afterburning, in other words, if I want to look at what's actually done to my fuel consumption, I don't take the ratio of my TSFCs. I take the ratio of my Fs. Does that make sense? And instead of 1.74, it's 3. 3 times as much fuel, okay? A 200% increase, okay? So 75% thrust increase and a huge benefit. 200% increase in fuel consumption, okay? You don't want to do this unless you have to, okay? The penalty is very great. It's very effective, but, okay, you don't want to do it, okay? So that's the point. Don't be deceived by the percentage increase in TSFC in terms of thinking that's the true cost of afterburning. You've got to look at the ratio of the actual change in F. Okay, does that make sense? So, what was I going to tell you all? Oh, the first year that I taught here, I had an F-14 pilot in my Thermo 1 class, and he and I finally connected, and I think that spring, the first time I taught here was fall '89, he was in my class, Thermo 1 class, and he just needed that one class, and I think that spring I taught propulsion, and we had connected, and he came and talked to my propulsion class about flying the F-14 and the propulsion system. I still have a bunch of his overheads from that plane. They don't fly that thing anymore, but that was the real workhorse fighter for the Navy for years. And I remember him saying that if he took off on the carrier completely loaded with fuel and arms and just left the afterburner on, just went out with accelerator all the way to the floor, that he would be out of fuel in 20 minutes. Those things can patrol. Those fighters of that nature for the Navy are designed to hang around for long periods of time. So, and that's why their engines are turbofan engines, by the way. Okay, for the extra fuel, the F-14 engine and other carrier engines on those jets are turbofan engines for the extra fuel economy, and then they get the super thrust they need when needed by afterburning. Homework 7. I can discuss next time the particulars and give a due date on it. It's very simple. If you get homework 5 right, you can just see it's an equation or two, and then I'm just going to have you run some cases, to look at the effect of afterburning temperature, okay, at cruise, and then look at I want you to look at the effect of afterburner at takeoff. Okay, and so we're going to basically put your altitude down to 0. And that changes some of your flight conditions, right, from your standard table. And then takeoff, your cruise Mach number would be 0, right? So you can do some calculations, right, on takeoff at sea level. Because that's where the afterburner is used so much, is for takeoff. So, you all are going to turn in homework part B, right? And my intent is to grade it and bring it back graded next time. That's my intent. And then discuss part C. So I'll be very unhappy repeating that discussion for people who don't come next time. So if you really want to hear whatever words of wisdom I might have for part C, you need to come next time. Okay? All righty.